Yeah.
I will start the translation. Now we are ready to start, and our first speaker in our Zoom session is Nicolai Reshetikhin, and his talk about spin Calogero-Moser system and two-dimensional Young Mills again. Well, thank you. Let's start.
You're welcome. So thank you for the introduction. Well, it's not just two-dimensional Young Mills again, it's revisited again. It has been revisited many times. And I gave this talk on Wednesday on the occasion of 70th birthday of Igor Frenkel. And it turns out that some of these results overlap with what Nikita Nekrasov and other people were doing in the 90s. So, and I think some of the people who are doing this are here, at least Sasha Gorsky is here, and yeah, I don't see anyone, everyone. So anyway, so this is the joint work with Jasper Stokman. So greetings to everyone from Tsinghua, from BIMSA. BIMSA is a new research institute which is welcoming anyone who wants to be in a good mathematical physics environment. So, yes, let's start. So the plan today is the following. First, I'll introduce quantum spin Calogero-Moser chains and as superintegrable quantum systems. So, and then we'll talk about two-dimensional Young Mills theory with open Wilson graphs. So, so first, classical superintegrability. I mean, to talk about quantum superintegrable systems without mentioning classical superintegrability is a little bit meaningless. So, so classical superintegrability is kind of a refinement of Liouville integrability in the framework of Hamiltonian mechanics. And it's, so let me remind it a little bit. So what is the Liouville integrability? I mean, physicists, mathematical physicists usually would phrase it like this. You have two n-dimensional phase space and n independent Poisson commuting Hamiltonians. So, but I mean, it can be slightly more complicated. There could be, say, n plus 100 Hamiltonians, and they're all connected by complicated algebraic equations. So I think geometrically, the most natural definition of an integrable system is simply a Lagrangian fibration, where the generic fibers are Lagrangian, but there could be some singular fibers. And typically, these are level surfaces of Poisson commuting functions. And, you know, we all know that there are many examples where there are singularities in fibers. So this is Liouville integrability with all the consequences. Now, what is superintegrability? Superintegrability is known by several names, and I was using before the name degenerate integrability that was designed by Nikhoroshev, who basically invented this modern framework of what superintegrability is. And then Mishchenko and Fomenko, they kind of rediscovered this phenomenon in the setup of Lie algebras and integrable systems related to Lie algebras. So they called it non-commutative integrability. And there is a good reason to call it non-commutative integrability. But then somehow Wojciechowski invented the name superintegrability, and it got stuck for no reasons, but it's just a good name. So superintegrability. So we have the phase space that is two n-dimensional, and we have two two Poisson projections. One is to 2n minus k Poisson manifold, and the other is to k-dimensional Poisson manifold with trivial Poisson structure. The generic fibers of the last projection, they are 2n minus 2k dimensional symplectic manifolds, and connected components of these generic fibers are generic symplectic leaves of this Poisson manifold. So then the generic fibers of the first projection, these are k-dimensional isotropic submanifolds. So these are the kind of analogs of Liouville tori. The difference is that in Liouville tori are n-dimensional, and these ones are k-dimensional, where k can be 1, for example. So you see, you can say more about the dynamics in this case. Say, for example, if k equals 1, then all trajectories are periodic. Okay, so again, typically level surfaces of 2n minus k independent functions that generate Poisson subalgebra, they are the fibers of the first projection. So that goes here, and again, that goes here. And this geometric setup is equivalent to the following algebraic setup. So in the Liouville case, you just simply have maximal Poisson commutative subalgebra in the algebra of functions on a symplectic manifold. In this case, you have Poisson subalgebra in the algebra of functions on the phase space. Let's call it, I'll call it J. And this is the subalgebra of conserved quantities. And then the other subalgebra is the algebra of functions on the lowest part of the projection. And this is actually the center of this Poisson subalgebra. So in general kind of Poisson algebraic framework, we have the Poisson algebra A with trivial center that corresponds to the functions on symplectic manifold. In this Poisson algebra, we have the Poisson subalgebra of rank 2n minus k. That's the maximal number of independent functions. And then the center of this Poisson center of this subalgebra should have the rank k. So it's very important to have this balance of dimensions. And when we have such thing, we can say that we have a superintegrable system. Any function from I will preserve these functions from J simply because I is the Poisson center. And so it will, independent functions from I, they will generate an affine coordinate system on fibers of this projection, affine coordinate system on these isotropic submanifolds. And this is the kind of action angle variables, action variables from the bottom, and the times of this evolution on the Liouville submanifolds. These are the angle variables. Okay, so this is the setup of classical superintegrability. In the quantum superintegrability, well, let's first start with quantum integrability. So again, everyone has its own kind of homegrown philosophy. So mine is that you cannot have quantum integrability without a classical one. Then you just have commuting operators. So it's meaningless to talk about integrability without kind of semi-classical context or some equivalent of this content. Say thermodynamic limit for spin chains can be considered as a semi-classical limit. So anyway, what is quantum integrability? Well, we have a deformation quantization of functions on our phase space. And in this deformation quantization, we have maximal commutative subalgebra. That's the algebraic setup. What's the algebraic setup for the superintegrability? Well, we have the same deformation quantization of the phase space, but now we have a deformation quantization of the Poisson subalgebra. It's an associative subalgebra in A, and its center as an associative algebra, and that's the deformation of the functions on B. It's a commutative algebra, so it's a commutative deformation. So this is the algebraic framework of superintegrability. And then we choose the representation space. That's just representation space of quantum algebra of observables. It's the same in both frameworks. And then here is the kind of spectral refinement of the definition of superintegrability is that this triple will say it's superintegrable quantum simple superintegrable system if each eigensubspace in H of the joint spectrum of our quantum Hamiltonians is an irreducible representation for our algebra J. So typical situation, for example, we have the universal enveloping algebra, we have its center, we have in the category of finite dimensional representations, what can happen? If the center acts by scalars, that means our representation is kind of a direct sum of several copies of irreducible representation. So in this case, we want to have just one copy. Okay, now this was the general setup, and I used up quite a lot of time. So, but without it would be more or less meaningless to move. So, so now let's consider very special superintegrable systems. I'll call them superintegrable spin Calogero-Moser chains. So visually, you can think of the following. Think of a space-time that is a circle with n marked points. Gauge fields are holonomies along the intervals between neighboring mark points. The gauge group is acting at the mark points, and it's the most natural action that is known, I think, to everyone. So you act by this n tuple of elements of the group on the collection of holonomies by this transformation that's called usually discrete gauge transformation. If you look at the microscope at this gauge transformation, you can see that it's a combination of two actions. It's the multiplication from the right and twisted multiplication from the left, twisted by the cyclic permutation on a circle. In principle, you can twist by any permutation. It's just that will not be a circle, and I don't know, maybe there are some interesting systems related to this. But here we will just do the circle. So both, I mean, not both, all three, in some sense, it's just two fundamental actions, and then the gauge transformation is just a diagonal action of two of them. But anyway, so all three of them lift to Hamiltonian action on the cotangent bundle to G to the n. So the quotient space, the cotangent bundle of G to the n over G to the n is a Poisson variety. So quotient with respect to the gauge action. The moment map, so because the action is Hamiltonian, we have moment maps. And we know what are the symplectic leaves for the Hamiltonian for the gauge quotient. So they are given by the of the gauge group. So in our case, the gauge group is G to the n. So coadjoint orbits are just products of n orbits for G. And so we have the Poisson maps. Our master Poisson manifold, symplectic manifold, T star G to the n. We can map it to G star to the n fibered product, G star to the n, using left and right moment maps. It's a fibered product over G star mod G to the n. In other words, points in the left copy of G star to the n and the right copy of G star to the n, they always live on the same coadjoint orbit. And then we can either naturally project to the left projection or to the right projection. It doesn't matter. I mean, the final answer will be the same, so I will choose the left projection. Okay, so we have these Poisson maps, but now we want to have a setup of a superintegrable system. So we want to have something that gives superintegrability. So if we will take the quotient, this cotangent model to G to the n, modulo the gauge action of G to the n, because these are all maps that are gauge equivariant, so it projects to the quotients. The quotient of G star to the n over the gauge group will be simply G star mod G to the n. And then we can choose the symplectic leaf in this quotient and apply the same Poisson maps, and we will get the so we have the surjective map from symplectic to Poisson, and then Poisson map to Poisson, but trivial Poisson. And it's not a complicated theorem to show that there is a right balance of dimensions, so we have a superintegrable system. So this is the classical superintegrable spin chain. So with Jasper Stokman, we have a paper that we started to write 2 years ago, and now I hope that we'll finish it this spring. Actually, spring is over, so this summer. So so this is the classical n-spin Calogero-Moser model. So now let's go to the quantum case. So in the quantum case, so we have the action of the gauge group on the group of the of parallel transports, or on the manifold of parallel transports that happen to be again G to the n. So infinitesimally, it means that we have a homomorphism of Lie algebras from G to the n to the vector fields on G to the n. And because we have 3 actions, we have 3 homomorphisms. And so in particular, we have the all these 3 homomorphisms. They give the embedding of the universal enveloping algebra to the associative algebra.
Коля, sorry, how do you see that this is Calogero-Moser spin model? And so spin is probably the rank of this orbit, and
yes, spin variables. They
just how to see.
I'll tell you this. It's not the 2 minutes answer. It's just.
But are there coordinates of Calogero particles?
Yes. So it's. Let me go to the quantum case, and then you will see the coordinates in the quantum case, and then it will be more clear. So anyway, it's in my mind. I'm sorry. We wrote this paper we didn't write it for 2 years. It was sitting for 2 years. So okay. Anyway, so there's a classical system. Now we're doing quantization. So we have 3 embeddings of the universal enveloping algebra into the algebra of differential operators on G to the n. Yes, so we can use left and right embeddings again. So this gives the embedding of the again, it's a fibered tensor product, and fibered in the following sense: the action of the center, it's fibered over the center to the power tensor power n. but it's sort of fibered in a twisted way. This is what tilde means. So we can move the central elements through this tensor product, but when we move them, Zn moves to the first factor, and it's all twisted by the cyclic twist as it should be. And in addition, we should apply the antipode. Okay, so this is the intermediate associative algebra, and then we can embed universal enveloping algebra either to the left copy or to the right copy of it in this fibered tensor product. Okay, so so this is, I mean, if you follow what I'm saying, this is the quantum analog of this. So if you take functions on these varieties, they will be embedded one into the other, and what is written here is just the quantization of them. Now let's take Gn invariant part in these algebras. So these are the Gn invariant differential operators on G to the n with respect to the gauge action. This is the G to the n invariant part of this tensor product of universal enveloping algebras. And this is simply the center to the tensor power n embedded, say, to the left factor. And it doesn't matter where it's embedded because it's the tensor product fibered over the center, so you can move it from left to right. So the gauge action is just the same that we started with, but kind of rephrased in the algebraic framework. And as I already said, this chain of algebras is the quantization of this embedding of algebras of functions on our Poisson varieties. So now let's construct an irreducible representation of the algebra of invariant differential operators. And this irreducible representation in the usual sense will be the analog of choosing a symplectic leaf in our Poisson variety. Okay, so I mean, from the general kind of philosophy of representation theory, we know that if we want to quantize the algebra of functions on a coadjoint orbit, we have to choose an irreducible representation, or rather sequence of irreducible representations, and endomorphisms of irreducible representations will be matrix algebras that quantize these Poisson algebras. So let's just do exactly this. So we choose n irreducible representations of G with highest weights mu1 un, and our Hilbert space will be L2 functions, gauge invariant functions with value in this tensor product. So gauge invariant means that they satisfy this gauge invariance condition. So every function is a vector in the tensor product of n representations. So G to the n naturally acts on this tensor product, and the action on the function from the left using this tensor product should be the same as the gauge transformation inside of the function. Plus this extra condition that every time one of the arguments is in the Cartan, the function should be in the zero weight subspace of the tensor product. Okay, so so now let's look more kind of carefully at this gauge action of G to the n on G to the n, and let's choose. It's not a section, but it's a partial section of this action. So for given G, so for given these holonomies, let's choose H in this very special way. But you see, we don't fix HI. So we still have this HI in G. I is somewhere from 1 to n. We fixed it. So then it's an easy computation to see that if you act on G by this particular H, what you will have is this element where all of the arguments, all of the holonomies are 1, and on the ith place, we have this conjugation. So this gives an isomorphism between G to the n mod G to the n and G mod G with respect to the conjugation. And if it's simple compact, then it's just H mod W. And we can forget about this regular part. Well, better not to actually. So very good. So we can think of the of this Hilbert space H mu. On one hand, we can think of this as gauge invariant functions on G to the n with values in the tensor product. Or we can think of these functions as W invariant, where W is the Weil group, W invariant functions on the regular part of the Cartan with the value in the zero-weight subspace of this tensor product. So I'm not saying the word quantum Hamiltonian reduction, but I could have said it several times here. So now we have this triple of algebras, the master algebra A, that's the algebra of G and invariant differential operators, and then these two subalgebras. I didn't say this, but it's easy to check that the subalgebra I is the center of J. And now we evaluate them on our Hilbert space, and that's the analog of choosing the symplectic heap. So now we have this chain of subalgebras. Now A mu is just the algebra of endomorphisms of H mu, and what's important now is that we have this subalgebra and its center. Now this is the subalgebra of quantum integrals. So quantum commuting integrals is generated by the Casimir elements, by the evaluation of the Casimir elements in our Hilbert space. And I will just to be specific, you can always choose the generators of the center as the Casimir elements, homogeneous elements of degree 2 and so on. These numbers are called exponents of simple the algebra. So altogether we have n times rank of G independent commuting operators. If the representations are big enough, if they are small, then we have less than this. So now one can compute these elements in the standard way. I'll skip the details. So this is the result of the computation of the second Casimir operator. So here Si is just the total spin, if you want, acting on this tensor product. It's a very special element with J equals I. I remember that we fixed I because we fixed this gauge symmetry in a very special way. So for other Casimirs, the expressions are more complicated, but there is a nice fact about all this is that, so in principle, you can easily compute all of them if you will take the operators, that is hk plus 1 second Casimir minus hk second Casimir. These are the so-called dynamical Knizhnik-Zamolodchikov equations where the z arguments are sent to infinity. So in some sense, you can call them topological. or you can call them asymptotical. These are the dynamical KZ equations where you use the constant dynamical R matrices instead of dynamical R matrices with variables Zi. So there is an explicit description of Hamiltonians. So now, what is the spectrum, joint spectrum of this
Sorry.
operators? Yes.
What label alpha?
Is this
Zero,
micro?
where it takes?
Can you say it again, because the internet somewhere?
Yeah, sorry, something. I'm asking about alpha. Your letter alpha, what it labels and where it takes values.
Oh, alpha, these are roots of G.
Roots of G.
G is a simple Lie algebra. For SLN, it will be
So all roots of G.
epsilon I minus epsilon J. What did you say?
No, thank you. And understand. So all roots. So this is usual QI minus QJ interaction. Yeah.
Yeah.
And Q is coordinate where in the.
It's on the cartan. So yeah, I wrote it somewhere here, but then I was very quick. So the adjoint action on the cartan on root elements is H alpha, and H alpha is e to the I Q alpha. So Q alpha, these are the kind of logarithmic coordinates on the cartan subgroup. And of course, they are periodic. Okay.
Okay.
All right. So now finally, strange. Okay. Joint eigenvalues of these Hamiltonians. So these are so-called trace functions. And again, some of these results are well known. For some of these, I couldn't find references. So I'm not giving any references now, but then I will mention prior works. So let's assume that we have highest weights of our simple Lie algebra, lambda I, such that they satisfy these iterative Clebsch-Gordan rules, and they satisfy them cyclically. So roughly speaking, we can say that like this: there is lambda, then there is mu I, and then lambda I minus 1, and every time we cross mu, the lambdas should satisfy the Clebsch-Gordan rule. So let's choose intertwiners from these spaces, and let's define endpoint trace function. This kind of trace functions were used for quite a while. I think they first appeared, well, in this setting, they first appeared, I think, in the paper by Ettingov, of Igor Frenkel, and Shurik Kirillov. But I'm sure they appeared earlier. So, these are some kind of cyclic versions of spherical functions. Okay, so you see the way how they work is the following: you take the product of holonomies, alternated with alternated product, and in between you sandwich it with intertwiners. So as a result, you get a vector in the tensor product of representations of G, and this vector has this kind of trace structure. So now our quantum Hamiltonians.
I'm sorry, but we have 5 minutes left.
Oh, okay. So so then quantum Hamiltonians, they act as central elements on the corresponding arguments. So it's very easy to show that on these trace functions, quantum Hamiltonians act simply by Casimers. So, and it's clear from everything else that we have the spectral decomposition of our L2 space into the eigen subspaces. So now the natural thing is to consider the propagator. So every time you have a quantum mechanical system, you have a propagator in time. Because you have n times the rank commuting operators, you can see the multi-time propagator. So in the Hilbert space, in the L2 Hilbert space, it's an integral operator with the kernel that is given by the spectral decomposition. And then slightly non-trivial fact that this kernel has the very simple integral representation which uses the partition functions for two-dimensional QCD. So it's the function that's given by this sum over all irreducible representations. So you have the character of lambda evaluated on the holonomy around this disk. And graphically, it just means the following. This is the representation of the propagator in terms of the spectral decomposition. To each region, you assign this exponent, and you assign the highest weight of G to each region. It's like in the interaction around the phase models. The other presentation is the integral representation, where you integrate over the holonomies corresponding to these insertions of Wilson lines, and you think of your cylinder as the cylinder where the Wilson lines colored by new eyes, they are running from one end of the cylinder to the other, and there are disks inserted in between them. And so this is a very inspiring picture. So now we want to consider the two-dimensional QCD with open ends where the Wilson graph goes outside of the disk. And same idea. So the partition function depends on holonomies around on the boundary edges, and you integrate over the holonomies inside. So if there is a representation at this corner, it's non-removable corner. You cannot do anything with it. If the representation is trivial, you can push this corner inside, it's a removable corner, then you can forget about the corners. So there is a gluing of such thing with the insertion of the Wilson line over here. So it gives this kind of Wilson line incorporated in the partition function. And it becomes the usual gluing in two-dimensional QCD if there is nothing in there and if there are no external lines. So basically, this structure is saying that you have 2-1-0 topological quantum field theory. So then there are observables in the usual way. And I want to finish this presentation. Well, unfortunately, I have 7 more pages, but I don't have time. So you can do the same thing with so-called open n-spin Calogero-Moser spin chains, where the gauge group is the same. You have holonomies along the intervals. The gauge group at the inner vertices is G, but the gauge group at the boundary vertices is K, where K is a subgroup in G. So the gauge group is this, the connections are this, and then one can easily show that this coset is the same as G mod K, another space that's very interesting and important in representation theory, and then blah, blah, blah. So the trace functions becomes the matrix elements functions. same here. The propagator now becomes this. So instead of the cylinder, you have the strip, kind of open-closed strings, as many physicists would say. So that's the formula for the propagator. And then this is what you can do with this. So you can construct Young-Mills theory with varying gauge groups. So, so here is the picture of the open-closed kind of surfaces. So you can have the Young-Mills theory on this in this setup, or more generally, you can have the following. Say if you have a disk with Wilson graphs that kind of go outside, Wilson graphs don't have to be connected. They can have several connected components. So you color each connected component with a subgroup of some master group G. You color each of the regions with a subgroup of G, and then when you have the border between one region and the other, so you have three groups: the gauge group for one region, the gauge group for the other region, the gauge group for the Wilson line, and then your effective gauge group is the intersection of these three groups, and this is where you have to integrate in order to get the partition function. So then there are natural questions. So what happens if the master group is SUN? And then you can ask many questions along these lines. So, and again, I didn't mention the existing bulk of work in this direction. So now, because there are outer representations mu I, we can send these highest weights to infinity. And then it becomes a meaningful semi-classical limit. So now the QCD can be studied in this semi-classical limit. There must be some beautiful relation to Chern-Simons theory. So we have a paper with Michael Pollack that we never put on the archive. This is from 1994 or 6 or 7, I don't remember, somewhere from back then. And then, of course, so there must be a very interesting line along here. And then another interesting line that I didn't mention here, it's the case when G is non-compact. Either complex non-compact or real, say, real split form of complexified G. Well, happy birthday, Lenya and Nikita. Well, thank you for the attention. Sorry, I think I went over time.
Thank you very much, Kola.
Well, thank you for the talk, and maybe time for one short question, not more.
Misha? No.
Okay, so maybe one comment. Actually, a very similar picture has been discussed in our papers with Nikita Nekrasov. We have related the Young-Mills theory, two-dimensional Young-Mills and Calogero system, and the open question, namely the relation to quantum Chern-Simons theory, has been discussed as well. And in that case, instead of Calogero, in a very similar setting, we have derived a Roisener system.
Yes, I know these papers. Nikita actually pointed out yesterday some archive unpublished review of him and pointed out your works. So yes, as you can see, there are minor. Well, it's sort of, you can say that this is a little bit further development because you didn't discuss superintegrability, which somehow completes the picture here. But many things were done back then, yes. So when the paper will come out, I'll give the proper references.
Thanks.
I completely agree with Sasha, yes. They have done very nice work.
Well,